Hey everyone, today we're going to talk about a pretty interesting topic, and it's the alveolar gas equation. And we're going to go in depth and apply it to the real world so we can really understand this equation in and out. And then at the end, I'll talk about the oxygen cascade and relate it to the alveolar gas equation. The equation is PAO2, and it's capital A for alveoli, equals FiO2, in brackets, your partial pressure of atmosphere minus your partial pressure of vapor pressure, minus, in brackets again, your PaCO2, and this is little a, which is arterial, divided by your respiratory quotient. So your FiO2 at room air is about 21%, so 0.21. Your partial pressure at atmosphere at sea level is 760 millimeters of mercury. Your vapor pressure, assuming that it's 100% humidity, is 47 millimeters of mercury at 37 degrees Celsius, which is around body temperature. And your arterial CO2 in a normal person is about 40 millimeters of mercury. And your respiratory quotient or respiratory ratio is around 0.8, and that's on a Western diet, but I'm going to explain that further when we get to it later in the video. So let's just plug in our normal numbers and calculate what our PaO2 would equal. So the first thing we need to do is let's figure out our brackets. So the first one, 760 minus 47 equals 713 millimeters of mercury. If you were to times that by 0.21, this would equal 149.73 millimeters of mercury, but we'll just round it up to 150. And then you've got to minus off the, in brackets, 40 millimeters of mercury divided by 0.8, which equals 50. So our PaO2 in a normal person at sea level, breathing normal room air oxygen and with a PaCO2 of 40 and on a Western diet would be about 100 millimeters of mercury. So this creates the pressure gradient that drives oxygen into the blood. But you can have issues with this where oxygen can't be driven into the blood, and that can be diffusion issues or gradient issues between the alveolar gas and the partial pressure of oxygen in the blood as well. But the way you can overcome a lot of these issues is by increasing the PaO2, and this is alveolar oxygen, which will then hopefully drive more oxygen into the blood to oxygenate the red cells as they pass by the alveoli. So let's just work through the equation and manipulate different steps to then be able to get the result we want by increasing the PaO2. So say you've got a hypoxic patient, and the first thing you're probably going to do is turn up the FiO2. So in this example, I'm going to make it 100%, which would just be 1.0. And if we go through our equation again, remember our brackets, 760 minus 47, 713. And then for our CO2 portion, it's going to be 50 millimeters of mercury. So we just do 1 times 713 minus our 50 millimeters of mercury, will equal 663 millimeters of mercury. So instantly, by just increasing the FiO2, I've increased the partial pressure of the alveolar oxygen. So that would probably be our first steps, or our first step when we come across a hypoxic patient is usually anyway to just turn up the FiO2. Let's go to the next step in the equation, which is our partial pressure of atmosphere. And you can have two branches of this. You can either have high altitude, which will decrease the partial pressure atmosphere, or you can decrease the altitude and that will increase the partial pressure. But really, you can only go to sea level, which is what we're normally at. But you can, in medicine, put people in a chamber and increase the pressure. So you can increase the partial pressure, which will increase the PaO2 as well. And I'll talk through these, but let's just start with the first example. So imagine for a moment you've been teleported to the top of Mount Everest, and the partial pressure at the top of Mount Everest is around 253 millimeters of mercury. So let's plug that into our equation. Now, if we were to work our way through the equation now, if you did 253 minus your 47, that equals 206. You then times that by 0.21 because we're not giving any extra oxygen, and the oxygen percent's still the same at the top of Mount Everest, it's 21%, equals 43.26. And then if you were to minus the 50 from the CO2 that's in our blood, you're actually going to be around -7 millimeters of mercury. So it's essentially, it's unsurvivable. But people do survive. So you have to ask, well, how do they survive? And there's adaptations that happen that help people to oxygenate their blood. So the first thing is that you're going to be breathing harder and breathing more. So you're going to lower your PaCO2, which means that you're going to have less taken off the equation. And people also take oxygen up to the top of Mount Everest with them as well. So let's just, for example, just for the sake of an experimental example, we're going to make our oxygen 50%, so 0.5, and we're going to breathe off half our CO2. So we've probably doubled our respiratory rate. And you can see here the way the equation works out is around 78 millimeters of mercury, which is survivable with training if you're fit and you have other adaptations in place that are going to help you maintain and store that oxygen in the body and pick up and carry more oxygen. But that's for another video where we'll talk about how oxygen is transported around the body. So let's go in the opposite direction now, and let's put someone in a barometric chamber, and we're going to double the atmosphere. So if we double the atmospheric pressure, that becomes 1,520 millimeters of mercury. If we were to plug in those numbers, work our way through the equation, and you're welcome to do this at home, but it would end up being 259 millimeters of mercury. So we've more than doubled the partial pressure of oxygen at the alveoli. And this is actually a form of therapy where you can put people in chambers like this and treat infections or treat people who are hypoxic, but it's more or less used for infections when people have anaerobic organisms, and also it helps with tissue breakdown, such as when people have flaps done and you need more oxygen to get to the tissues. You could put people in one of these chambers to then increase the partial pressure of oxygen, which has a downstream effect which will become relevant when we talk about the oxygen cascade, helping there be a higher oxygen partial pressure at the tissue level as well. So in green here, we've got our vapor pressure. Now, vapor pressure is largely fixed because when you get to about 3 centimeters above the carina of the lungs, and the carina is the point where the trachea splits and you have the left and right main bronchus, and it's just at the bottom of that. At about 3 centimeters above this, at 100% humidity at 37 degrees, the partial pressure of the vapor is about 47 millimeters of mercury. And remember, this takes up some space in our air, so it lowers our oxygen carrying capacity off the air that's brought into the lungs, but it's largely fixed, so we can't really change that. So second last, let's talk about the PaCO2. So in this example, what I'm going to do is I'm just going to double the PaCO2. So the assumption is here that either CO2 production has gone up, meaning that your tissues are producing more CO2 and you're just not clearing it, or you have reduced your respiratory rate, so you're just not clearing it. So what's being made isn't being breathed off. So if we were to double it, it would be 80 millimeters of mercury, and we divide it by 0.8, it equals 100 millimeters of mercury. That first part of our equation equals about 150 millimeters of mercury, so you minus your 100. So our PaCO2, just with a doubling of the CO2, has halved our PaO2. So the CO2 has actually taken up space in the alveoli. And I'll explain why in a minute when we talk about the respiratory quotient, because obviously we're talking here about the arterial CO2. The respiratory quotient is a ratio, and it's CO2 produced to oxygen consumed. And it actually represents at the cellular level. And respiratory exchange ratio is the exchange of CO2 produced with oxygen consumed at the level of the alveolus, or at the level of the mouth is where it's measured. So respiratory quotient and respiratory exchange ratio are actually the same when they're steady state. So when the amount of CO2 produced is constant and the oxygen consumed is constant, they will equal each other. So for the sake of just saving a bit of time, I'm just going to talk about respiratory quotient. And respiratory quotient is affected by the fuel that your cells use. So if your cells were to use just glucose, the respiratory quotient would be 1.0, meaning that for every CO2 produced, 1 oxygen is consumed, so it's an equal ratio. And then for protein, it's 0.8, and then for fats, it's 0.7. And before I said a Western diet is 0.8, and it's not because the Western diet is full of protein and we're all bodybuilders and able to, have huge muscles or anything like that. It's actually because the Western diet's mostly made up of glucose and fats. So it's around 0.8 is what it equals out to. So I'm just going to put in the example someone or cells that are only using glucose as an energy source. And if we work our way through the equation, so the first part of the equation with our oxygen, partial pressure atmosphere, and partial pressure or vapor pressure equals about 150. So then you just minus 40 because the ratio is just 1.0. So 40 divided by 1, it equals about 110 millimeters of mercury. So an all glucose diet would essentially lead to technically a increased PaO2 in the alveolus. Now let's change it to a diet that's completely just fats. And if we were to work our way through the equation, the PaO2 would equal 93 millimeters of mercury. And so just to reiterate the point, the respiratory quotient, although it represents the cellular level, it's equal to the respiratory exchange ratio as long as everything is at steady state. And the respiratory exchange ratio is showing us, how much CO2 is coming out of the blood versus oxygen going into the blood. And that's why that ratio is important here in this part of the equation. All right, so the last part, I'm just going to relate it to the oxygen cascade. And this is a concept that you might get asked to draw in exams. And I find if you understand the alveolar gas equation, you can pretty much work out and understand the oxygen cascade. So first step of the oxygen cascade is inspired dry air. And this is made up of whatever the FiO2 of the surrounding air is times the atmospheric pressure, right? It makes sense, it's dry, it's just dry air sitting in the atmosphere, which equals about 160 millimeters of mercury. Then it steps down and we talk about humidified air, and this is air that's now entered the lungs essentially. And this is made up of the 3 components, FiO2, the atmospheric pressure, and the vapor pressure. And then we move on to the alveolar partial pressure, so PaO2, and this is capital A. And now we need to take into account the amount of space that the CO2 is now taking up in the alveolus. So our PaO2, after taking into account the CO2, is about 100 millimeters of mercury. So now we move beyond the alveolar gas equation and we move to the arterial oxygen. So this is how much from the alveolus has gotten into the arterial blood. And this is about 95 millimeters of mercury. And so this gap, this difference between the alveolar partial pressure and the arterial partial pressure is called the AA gradient. And this is capital A for alveolus to little a for arterial gradient. And this gradient will exist in everyone, and it's usually around 5 millimeters of mercury, and it's caused by things like shunt. So you have physiological shunts that happen. There can be diffusion defects as well, and VQ mismatch as well that can cause this gradient to increase. Now, we drop down as we get to our cells, and there will be some blood that will bypass and go around, and then we'll continue on, and then some other blood that will go to the cellular level and get to the mitochondria. And it's got quite a large range because it depends on cellular metabolism, and it's between about 4 and 22 millimeters of mercury at the mitochondria. And that 40 millimeters of mercury is what you would see in venous blood as it's returned to the lungs. So a key thing to mention here for bonus points, if you're aiming for full marks talking about the oxygen cascade, would be to talk about the Pasteur point. So at about less than 1 millimeter of mercury, this is called the Pasteur point. And at this point, the partial pressure is so low that the mitochondria cannot even use the oxygen that's reaching the cells. So you're going to have, the mitochondria just will not function at all with oxygen. And it's important to mention this because everything leading up from the top of the oxygen cascade on our far left, going down to the mitochondria, at the end of the day, the reason why we breathe is we want to get rid of CO2 and give oxygen. So we need, if we improve all the numbers that happened before reaching the mitochondria, we can increase the partial pressure that reaches the mitochondria and stop cellular hypoxia. Hence why when I mentioned before the importance of modifying all of these, it's not just about getting our alveolar oxygenated, it's also about getting all of that oxygen to the cell so the cell can go through its normal aerobic metabolism. So quite a long video, and I thank you for watching, and I really appreciate if you guys give me any feedback at all that you recommend. In my next video, we're going to talk about oxygen carrying capacity of the blood and relate it back to this.